The ocean is just, well, it's this incredible force, isn't it? Even the biggest ships, they can feel pretty small out there when the waves pick up.
Oh, absolutely. And that's been the challenge forever, really, trying to build something that can handle those forces.
It's this constant dance between engineering and nature.
It really is. I mean, making something float is, well, one thing, but making it move smoothly, efficiently, keep people safe and comfortable, especially when the sea gets rough. That's a whole different level. That's where the real naval architecture comes in.
Yeah, exactly. And that's what we're diving into today on The Deep Dive, brought to you by the All Sorts podcast. We've gathered a whole load of material research papers, technical articles, even some forum discussions.
All looking at the latest advances in ship stability and performance. So think of this as your guide to how engineers are making ships better at handling the sea.
Our mission really is to pull out the key takeaways from all this info for you.
Right. So where do we start? I guess the basic problem. A ship moving through waves.
Yeah, the sources call this seakeeping, right? How well the vessel handles the conditions.
Exactly, seakeeping. And it's not just about, not sinking.
No, it sounds like much more. The sources really stressed the difference between just surviving and actually being able to do its job, like maintaining speed or using equipment.
Or keeping passengers comfortable. Motion sickness is a surprisingly big factor driving a lot of this research.
I can imagine, especially for ferries or cruise ships,
Uh-huh.
but also for crew effectiveness, right?
Definitely. You don't want your crew feeling unwell or overly fatigued. It impacts safety and operations.
Something I found interesting in the sources was how seakeeping used to be handled in the design process. It often came quite late.
Yeah, that's the traditional design spiral approach.
Well-
You'd sort of design the main hull, the structure, the machinery, and then analyze how it would behave in waves.
Which seems less than ideal.
Well, it made it harder to make fundamental changes if the seakeeping wasn't great, especially if you were trying something new, like an innovative hull shape where you didn't have decades of past experience to rely on.
Ah, okay. So integrating that analysis earlier is a key shift mentioned in the sources.
A really crucial one, yeah. Now, to actually talk about how a ship moves, we need some standard terms.
Right. The sources mention the 6 degrees of freedom.
Exactly. It's how engineers describe every possible motion. Think of it in 3D space. You got 3 linear movements, like sliding along axes.
Okay, like forward and back.
That's surge, front to back motion. Then there's sway, which is side to side. And heave, that's the straight up and down movement.
Surge, sway, heave. Got it. Forward, back, side, up, down. What are the other 3?
Those are rotations. Roll is the one most people think of, the side to side tilting.
A rocking motion.
Yep. Then pitch is the front to back tilting, like a seesaw.
Hmm.
And yaw is the rotation around the vertical axis, basically turning or spinning.
Heaves, sway, surge, roll, pitch, yaw. That covers everything. So what makes a ship do more or less of these things in waves? What factors did the sources highlight?
Well, a whole bunch of things. Size is obviously a big one. Bigger ships generally feel the waves less, relatively speaking.
Okay.
Displacement, the ship's weight matters too. A heavier ship usually has lower motions for the same amount of wave energy pushing it around.
Right. Inertia.
Exactly. Then the actual dimensions, the shape of the hull, how the weight is distributed inside, it all plays a huge role.
And stability itself. The sources mentioned that had a sort of counterintuitive effect sometimes.
Yeah, that's a really key point. A ship that's designed to be very stable, meaning it resists rolling strongly, will tend to follow the slope of the waves more closely.
It tilts with the wave.
More readily, yes. Which can actually lead to higher accelerations, that quick snapping motion, which can feel uncomfortable. But the overall amplitude, how far it actually tilts, might be less than a less stable ship.
So it's a trade-off between how fast it moves versus how far it moves.
Precisely. And of course, freeboard, the height of the deck above the water, that's crucial for keeping water off the deck. Simple but important.
Okay, so it's complex. How do engineers actually predict this stuff before a ship is built? How do they assess the seakeeping?
The sources laid out a kind of 3-part framework they use. First, you have to understand the sea environment.
Meaning the waves.
Yeah, characterizing the waves the ship is likely to encounter. Using things like wave spectrums to describe the mix of wave heights and periods.
They define the challenge. What's next?
Second, you need to predict the vessel's response to that environment. And this is where a really critical concept comes in. Response amplitude operators, or RAOs.
RAOs. Okay, that sounds technical. What's the core idea there?
Think of them like a ship's fingerprint for waves. For each specific wave frequency and direction, the RAO tells you how much the ship will move, how much it will roll, pitch, heave, whatever per unit of wave height.
So it translates wave input into ship motion output?
Exactly. It's a transfer function. And the insight is, if you know the RAOs for all frequencies and you know the wave spectrum described in the sea state, you can combine them using math linear superposition to predict the overall ship motion in that complex, random-looking sea.
That's clever. It turns chaos into something you can calculate.
It's a very powerful tool. And the third part of the framework.
That's the vessel's mission and criteria. What does the ship actually need to do, and what are the limits on motion for that?
Right. And this is where things get, well, complicated, as the sources pointed out.
How so?
Because the acceptable limits vary massively. A container ship cares most about things like added resistance, fuel efficiency, structural loads. A ferry or cruise ship, passenger comfort is king, minimizing those vertical and lateral accelerations that cause seasickness.
And a warship might need a super stable platform for launching helicopters or firing weapons.
Exactly. So the criteria are totally different, and this makes comparing designs tricky. There isn't one single definition of good seakeeping that fits all ships.
So optimizing for one thing might make another worse.
Sometimes, yes. And even for something like passenger comfort, the sources mentioned that small changes in assumptions, like how long people are exposed to the motion, can change whether a design meets the criteria or not. It's not always black and white.
That lack of universal criteria seems like a real challenge when comparing different designs, especially new ones.
It absolutely is.
Yeah.
It makes it hard to say definitively this design is better without specifying better for what.
Okay, so you've got the environment, the predicted response using RAOs, and these often subjective criteria. How do engineers actually generate those predictions? What methods do they use?
Well, the sources mention a few key approaches. First, just prior experience with similar ships. That's always a starting point.
Sure, learn from the past.
Then calculation and numerical simulation. This is huge today.
You mean things like CFD, computational fluid dynamics?
Yep. CFD is very powerful. It involves solving complex equations like the Rand's equations you might hear about to model the fluid flow around the hull in detail.
Sounds computationally expensive.
It can be. For quicker analysis, especially earlier in design, they might use simpler methods like strip theory. That's a frequency domain method. Faster, but with more assumptions and limitations. There are also time domain simulations for tackling more complex, nonlinear stuff like large waves.
So, lots of computer modeling. What are the pros and cons?
The big advantage is you can test lots of design variations relatively quickly and cheaply compared to building physical models. But, and this is a key insight from the sources, these numerical methods aren't perfect.
They still need checking.
Absolutely. Physical model tests and specialized wave tanks are still essential for validation, especially for new hull forms or complex phenomena that the simulations might struggle with. And ultimately, measurements on the real ship are the gold standard.
So it's a cycle. Simulate, test, refine, maybe test again.
Exactly. Simulation helps explore the design space, physical testing provides the crucial reality check, and validation data. It's this combination that drives innovation.
Speaking of innovation, let's talk about specific technologies. The sources spent quite a bit of time on something called the hull vane.
Ah, yes, the hull vane. Really interesting piece of kit. It's basically a fixed underwater wing attached near the stern at the transom of the ship.
Like a hydrofoil.
It looks a bit like one, but the sources were clear. Its main purpose isn't to lift the whole ship, especially not for displacement hulls traveling below planing speeds. Its main goals are reducing resistance and improving seakeeping.
Okay, so how does it work then? How does a wing underwater reduce resistance?
It's pretty clever. The wing generates lift and drag, like any foil. But because of the way water flows up and under the stern of many ships, the hull vane is positioned and angled so that the lift source it generates actually has a forward component.
So the lift is partly pushing the ship forward.
Exactly. It creates a small forward thrust, effectively counteracting some of the ship's resistance. Plus, it modifies the wave pattern coming off the stern. It reduces the size of the stern wave, which also cuts down on wave-making resistance.
Like a bulbous bow, but at the back.
Sort of, yeah. Similar principle of wave cancellation. And the sources emphasize that these vanes are highly optimized using CFD for each specific ship. It's not just bolted on.
Tailor-made for the hull.
Definitely. And the results they presented, comparing it to traditional things like stern wedges or interceptors, were pretty impressive.
What kind of numbers did the sources mention?
For resistance reduction, one study showed around 13% less resistance at a typical transit speed and up to 15% less at top speed for the patrol boat they tested.
Wow, that's significant fuel savings right there.
Absolutely. And the reduction in propulsive power needed was even bigger, because the vane also improves the flow into the propeller. They reported something like 11% less power needed at transit and over 19% less at top speed.
That's huge. But you said it helps with seakeeping too.
Yes, the model test showed clear benefits there as well. Pitch motion, the seesaw movement, was reduced by between 3% and 11%, depending on the wave conditions.
Less pitching is definitely good for comfort.
And roll motion saw reductions too, up to 17% in certain conditions like stern quartering seas, where ships can often roll quite heavily.
Better stability. What about accelerations?
Reduced as well. They measured about 6% lower vertical accelerations on the bridge and around 10% lower on the helicopter deck and head seas. That makes a real difference for crew comfort and the ability to operate equipment.
And wasn't there a really dramatic number about slamming?
Yes. This was striking. Slamming pressures, the impact force when the bow crashes down into a wave, were reduced by over 50% in head seas. That's massive for reducing stress on the hull and improving comfort in rough weather.
So better efficiency, better comfort, less stress on the ship, all from this one fixed wing. Are there downsides? Integration challenges?
The sources did mention practicalities. You have to position it correctly, obviously, and integrate it structurally. And particularly for naval ships, you need to make sure it doesn't interfere with things deployed from the stern, like towed sonar rays or small boats.
Makes sense. You can't block other equipment.
Right. But the analyses suggest it's usually manageable with careful design. And sometimes the vane might even help stern operations by damping the ship's motion and reducing wake turbulence.
Interesting. Any future developments mentioned for the hull vane?
They touched on the idea of an active hull vane, maybe working together with a T-foil near the bow. The idea would be to dynamically adjust the forces to get even better sea-keeping control, potentially shifting the ship's effective pivot point.
Fascinating. So the hull vane is passive, but they're also fully active systems, right? Ride control systems.
Exactly. Ride control systems, or RCS. These use actively controlled surfaces or devices to continuously dampen multiple motions: roll, pitch, yaw, heave, sway, all at the same time, reacting in real time to the waves.
What kind of devices make up an RCS?
The sources listed quite a few. Active T-foils near the bow, like just mentioned. Trim tabs or interceptors at the stern. These are like small adjustable flaps. Lifting foils, active stabilizer fins like the ones you see on cruise ships, but maybe more sophisticated active rudders, even things like air cushions on some high-speed craft. They can be used alone or all integrated together.
And the goal is essentially super smooth sailing.
Pretty much. The benefits listed are reduced motion sickness, less crew fatigue, fewer accidents, less risk of cargo damage. Plus, by keeping the ship at an optimal trim or attitude, they can also improve speed and fuel efficiency.
And these aren't just experimental. The sources mention widespread use.
Oh yeah, widely used on fast ferries, luxury yachts, and lots of naval vessels. One source noted a particular brand is used by navies in over 50 countries. So definitely established technology.
Okay, so we've talked about analysis and we've talked about add-on devices, passive and active. What about the fundamental hull shape itself? How much does that dictate seakeeping?
A huge amount. And the sources use the trimaran as an example here.
A ship with 3 hulls.
Right. Multi-hulls like trimarans are getting more popular for certain applications, but compared to traditional monohulls, there's less historical data and fewer tried and tested design tools specifically for them.
So it's harder to predict their behavior.
A bit more challenging, yes. Though the studies mentioned do suggest trimarans can potentially offer better seakeeping, particularly less roll and maybe pitch, compared to a monohull of similar size. That's one of their main attractions.
But applying the standard analysis tools, like strip theory, is more complex for them.
It is. Strip theory works best for slender, ship-shaped forms. Applying it accurately to the 3 interacting hulls of a trimaran requires modifications and careful validation. Research is ongoing there.
And this brings us back to the criteria problem, doesn't it? Comparing a trimaran to a monohull.
Exactly. This is a strong point in the sources regarding multi-hulls. How do you make a fair comparison? If you're designing a fast ferry, maybe comfort is paramount, defined by acceleration limits. But as we said, those limits can be debated.
So one design might look better based on one set of comfort criteria, but worse based on another slightly different set.
Precisely. Or maybe the trimaran has lower motions but higher structural loads in certain conditions.
Here.
There's no single best answer without defining the mission and the exact comparison metrics very carefully. It makes optimization complex.
It really highlights how much context matters in ship design.
It does, and it underscores why, even with improving simulation tools for complex shapes like trimarans, physical model testing is still vital to capture things like the effects of waves passing between the hulls or predicting drag accurately. Some things are still hard to model perfectly.
It seems like there's still so much to learn and refine, even with all the technology. Let's shift perspective again. Looking ahead, how does all this connect with, say, autonomous ships?
That was a really interesting thread in the forum discussions we looked at. The core idea is that an autonomous ship needs some way to feel the sea, to understand how it's interacting with the waves.
Not intuition like a human captain, but data.
Exactly. Lots of data from sensors all over the ship measuring forces, stresses, bending moments, accelerations. This data feeds into the autonomous control system.
Why is that so critical for autonomy?
Because the system needs to make decisions to keep the ship safe and operating within its limits, especially in bad weather, without a human crew to intervene directly based on experience or feel.
The sources even suggested autonomous ships might need stricter operating limits than manned ships.
That was the argument, because you lose that nuanced human judgment for unexpected extreme situations. So, the autonomous system might be programmed with wider safety margins, relying purely on sensor data and predictive models.
So even with advanced weather forecasting telling the ship where not to go, the physical interaction with whatever waves it does encounter remains critical.
Absolutely. The sea is still the sea. And the need for highly reliable, accurate data on the ship's response for these autonomous systems will likely drive further improvements in seakeeping science and sensor technology.
It sounds like a feedback loop. Better understanding enables autonomy, and the demands of autonomy push for even better understanding.
That sums it up well, I think.
Wow, okay. We have really journeyed through quite a bit here in this deep dive.
Right.
From just the basic physics of waves hitting a ship
To how engineers break down those motions into 6 degrees of freedom and use sophisticated tools like RAOs and CFD to predict behavior.
and then exploring actual hardware solutions, things like the hull vane, offering passive gains in efficiency and stability,
And the active ride control systems using foils and fins to dynamically smooth the ride.
plus considering how fundamental hull shape, like with trimarans, impacts everything, and the real challenge of defining what good seakeeping even means across different missions.
Yeah, that complexity of criteria is a recurring theme. But underlying all of it, the goal seems consistent. Tame the motion, boost efficiency, improve comfort and safety, make the ship more capable.
Whether it's for passengers, cargo, naval operations, or these future autonomous vessels.
It's this blend of advanced simulation, essential physical testing, and clever engineering that's making it happen.
So after exploring all this, what does it mean for you, our listener?
Well, here's a thought to take away. As technology gives us ever more power to predict and even control how a ship moves in the water, will our very definition of seaworthy or comfortable keep changing?
And thinking about those autonomous ships, how will their absolute need for precise, reliable data push the boundaries of seakeeping science even further? Something to ponder, perhaps, next time you see a vessel navigating the waves.
Definitely food for thought.
Okay.
And as we navigate these complex waters of knowledge together here on the Deep Dives, brought to you by the All Sorts podcast, we really rely on signals and insights from you, much like a ship needs to understand the sea state.
Absolutely. So if you found this exploration of ship stability and performance useful, or if it sparked your curiosity about the engineering that shapes our world, think of engaging with us as catching a favorable wind for the All Sorts podcast.
Yeah, set your course for more discoveries. Liking this particular deep dive sends a signal out, helps others find it if they're interested in this kind of stuff.
And sharing it helps spread that knowledge to other learners, people who appreciate getting into the details of how things work.
And please, subscribe to the All Sorts podcast on YouTube. That way you won't miss our next exploration into Rextaval. Well, whatever fascinating topic we dive into next. Plus, you can find all our previous deep dives wherever you usually get your podcasts.
Loads of different subjects to explore there. And to stay connected with our journey, our community, you can follow All Sorts Podcast on X, Instagram, and Threads. Your likes, shares, subscribes, follows, they genuinely help us chart the course for future deep dives.